In an earlier lecture, we've seen the notion of an isomorphism of groups. Now in this lecture, I'm going to talk about homomorphisms of groups. It's a slightly more general notion given to groups G and H. A homomorphism from G to H is a function f from G to H, which basically takes the group structure of G and transfers it to the group structure of H, namely f of G1, G2 is f of G1 times f of G2 for all G1, G2 in G. Okay, so let's look at some basic properties of homomorphisms. So the most fundamental property of a homomorphism is that it must take the identity of G to the identity of H. So f of identity of G is equal to identity of H. And why is this true? Well, so f of identity of G is equal to, well, identity of G is identity of G into identity of G, right? So it's equal to f of identity of G into identity of G. And then using this homomorphism property here, what we get is it's f of identity of G into f of identity of G. So f of identity of G is an element of H, and this element has a property that it is equal to what you get when you multiply it by itself. And now remember, in groups we have this cancellation property, so this implies that f of identity of G is equal to identity of H. You just cancel out this here with this here. Okay. Now another property of group homomorphisms is that they preserve inverses. Okay, so f of x inverse is equal to f of x inverse for every x in G. I leave this as an exercise for you. Okay, it's fairly straightforward. And let's look at some examples to get a feeling for this. So look at the group Z with addition, and take H to be the group Z mod NZ, residue classes mod N with addition. Then F taking an element G or maybe X goes to its residue class mod N, which I'll write X plus NZ, is a homomorphism. This is a straightforward consequence of the way addition is defined in the group Z mod NZ. So I won't say too much about it. Okay, so that's one example. And here's another example from linear algebra. So you take G to be the group of all matrices A, say n by n matrices, let's say with real entries, such that determinant of A is non-zero. Then we know that if determinant of A is non-zero, then A is an invertible matrix. So this forms a group under multiplication, under matrix multiplication. And you take H to be the group of non-zero real numbers under multiplication. Then F G to H defined by f of A equals determinant of A is a homomorphism of groups. Now let's look at a slightly more interesting example. We already know about this group Sn permutations on n letters. Now I'll define a homomorphism from this to the group of the previous page. Let's give this a name. So let's call this group, well, so G, when I say G, I'm going to talk about this group G of invertible matrices, n by n matrices with real entries. Okay, and so G equals A belongs to M and R such that determinant of A is non-zero. So that's a group under multiplication. And I'm going to define it the following way. So, so let EI in Rn be the vector given by 0, 0, 0 everywhere except for a 1 in the ith row. It's just a column vector with a 1 in the ith position. So E1, E2, E3, these are all basis vectors for Rn, if you think of them as column vectors. And so given a permutation W in Sn, define EW to be the matrix. I'll give it as a block matrix. The first column of this matrix is EW1. The second column is EW2, and so on. Okay, so let's just take an example here. So take n equals 3. Take W to be the permutation 2, 1, 3. So that means W1 is 2, W2 is 1, and W3 is 3. Then what is EW? EW is the matrix whose first column has 1 in the second row, the second column has 1 in the first row, and the third column has 1 in the third row. Okay, so I claim that this is a group homomorphism. To prove this, we'll just show that if we take, so we want to show that, so that we're calling this map W goes to EW. Let's give it a name. Let's just call it F. So we need to show that F of W1, W2. So we need to show that this is F of W1, F of W2. Or in other words, E subscript W1, W2, is this equal to EW1 multiplied by EW2? Now this EW1 multiplied by EW2 is an n by n matrix. And EW1, W2 is also an n by n matrix. We want to know if these n by n matrices are equal. So what we can do is, we can check if EW1, W2 multiplied by EI, this column vector with 1 in the ith row, whether this is equal to EW1 multiplied by EW2 multiplied by EI. Okay, so this is what we need to prove. For all I, 1 to n. But the point is that EW times EI is just E subscript Wi. You can check this by using matrix multiplication. So EW1 EW2 times EI is EW1 times W2 times EI. Well, that's EW1 EW2I, but that's EW1 W2I, which is the same as EW1 W2 EI as claimed. Okay. Now I'll end this recording with by listing a few basic properties of homomorphisms. So the first, rather obvious, is that a homomorphism is an isomorphism if and only if it is a bijection. Okay, so what I'm saying is that isomorphisms are bijective homomorphisms. That's more or less from the definition of an isomorphism of groups. Okay. Secondly, for any group G, the identity map I from G to G. So this is the map which takes I of X to X, is a group homomorphism. So I'll say homomorphism or group homomorphism interchangeably. You'll see later in this course that there are other kinds of homomorphisms. And if F is a group homomorphism from G to H, and G from H to K is another group homomorphism, then G circle F from G to K is also a group homomorphism. Okay, I'm sure you can check all of these properties quite easily by yourself, so I'm not going to go into the proofs. Instead, I'll give you some exercises on the homework which will help you solidify your understanding of group homomorphisms.